Alright, so in the last class we were trying to develop the language of chemical potentials, right. So, the small g's mu1, mu2, right, to understand phase diagrams. Once we start changing the number of species, right, so that constitute a phase, okay. And so that leads us to the idea of what is called solution thermodynamics, and we have defined so we said that okay, I will look at compositions of so essentially I will stick to so in this course we are going to stick to what are called binary solutions, which means there are only 2 species, right. You can add more species, it is just going to slightly complicate the math, but the physics is going to be more or less similar, right. So, binary, ternary, quaternary and so on and so forth, right. So, the way thermodynamics develops is going to be the same, right. So, binary gives us a good idea of how these phase diagrams can be constructed. So, I am just going to look at species, 2 species that sort of come together, form solutions, or that separate out and then undergo these phase transitions and so on, okay. So, having said that, we have said alright. So, let us actually first look at what is called average Gibbs free energy, right. So, Gibbs free energy is what we are going to look at from now on, forget all the other free energy quantities that we have defined, right. So, average Gibbs free energy at a given temperature, pressure, right, and that I am going to say that it is Gibbs free energy G, capital G, divided by N, right. So, N is the total number of molecules that make up this phase, okay. So, it does not matter how many, what molecules, what percentage of which species is coming. So, I add N1 and I add N2 and then I say G equal to capital G by N, right. So, this is in binary solutions, right. So, let us go back and say that look, this G being equal to capital G by N, this is in binary solutions. I mean this is generally valid, but so I am going to just look at binary solutions, okay. And if I then say alright, but then let us further fine grain it, right. So, G equal to capital G by N, that is okay, but what information is it going to give me, what does it constitute of, because my G should come from species 1 as well as species 2, right. Now, species 1 has a chemical potential, species 2 has a chemical potential, which means I add one more molecule of species 1 to my phase, then so it releases some energy, that is mu 1. I add one more molecule of species 2 to my phase, then that releases some energy, that is mu 2, right. So, these are well defined, mu 1s and mu 2s are well defined. So, in terms of mu 1s and mu 2s, can you tell me what G is, and that is just x1 times mu 1 plus x2 times mu 2, right. And these curves look so I like I said so I think this is concave lens is this, convex is this, right. So, this is convex, not concave, right. These are convex and they are pointing down, right. So, this is how typically you will see these G versus composition curves look like, okay. So, now if I then so let us try to understand graphically, right. So, what is all this, so if I give you a graph that just says G of alpha, right. So, G in an alpha phase, right. So, alpha being so let us look at one phase and then look at the phase competitions and things like that, right. So, G of alpha as a function of x2, that is going to look somewhat like this, right. So, I said it is going to be convex down, right. So, let me change the color here, okay. And from here I am going to ask you the question, what is mu 2, right. So, can I just mu 2 of alpha, can I read off mu 2 of alpha from the above phase diagram? Now, remember, how did we define mu 2? Mu 2 is the change in the total Gibbs free energy. This is Gibbs free energy, not the average Gibbs free energy, right, when I change N2, okay. So, this is how we define mu 2 as, okay. Now, or in other so mu 1 is also equal to dou G by dou N1, okay. So, that is so in terms of, we want to write everything in terms of small g's now, that is dou N small g by dou N1, okay. All right. Now, so if I have a plot of G versus capital N1 or capital N2, right, now then I can just say that okay, mu is the slope of that, right. So, for some curve which looks like this, I can say that mu 2 is just the slope of this, okay. But I do not have a curve of G versus N2, I have a curve of small g versus x2, right, and I am saying that small g is just dependent on x2, it is not dependent on n, right, but capital G is dependent on capital N, right. So, I want to write everything in terms of small g and x2, and in a curve that consists of small g and x2, how do I extract the mu's, right. So, that is the question that we are asking. So, how can I extract mu's? How can I graphically extract mu's, mu1 and mu2 from G, small g versus x2 curves, okay. So, this is going to be an important exercise in all of solution thermodynamics. So, just bear with me here. So, mu1 is, let us say, let us go back to mu1 dou g by dou n1, that is dou n small g, right. So, capital G is n small g, that is how we define small g as, by dou n1, okay. Now, I will just do by parts, and I am going to say this is dou n by dou n1 plus n times dou g small g by dou n1, right. Remember that g is just dependent on x2, it is not dependent on capital N, right. So, let us keep that in mind. Now, so n is nothing but n1 plus n2, right. n1 and n2 are independent, n1 and n2 are independent, it is not like x1 and x2. x1 and x2 are dependent in that x1 plus x2 is 1, but n1 and n2 are independent, right. So, I am not normalizing it with anything, n1 and n2 are independent. So, dou n by dou n1, which means I just change n1 and I see what is the change in n. I do not change n2, I keep n2 a constant, and that should be equal to 1, okay. So, so this is a quantity that is 1. So, this will just be equal to g, or let us write 1 is equal to g plus capital N times, now dou g by dou n1, now I want to write it in terms of x2s, right. I am going to write it as dou g by dou x2 times dou x2 by dou n1, right. So, how does n1 change by changing x2? So, that those are the sort of questions that we are asking, okay. Now, that is equal to g plus n times dou g by dou x2 times dou x2 by dou n1, alright. And we have this relation that x2 equal to 1 minus n1 by n, right. Okay, so, we have this relation x2 is just 1 minus x1 or 1 minus n1 by 1. So, I want to find what dou x2 by dou n1 is, and dou x2 by dou n1 is simply so minus dou n1 by n by dou n1, okay. And that so if I do integration by parts, I have dou n1 by dou n1, and that is 1, right, minus n1 times dou 1 by n by dou n1, sorry, dou n1, okay. So, that will be minus 1 by n plus n1 by n square, right. So, this is a minus 1 by n square comes in the denominator, and so I have n1 by n square, right. So, and that turns out to be so 1 by n n square, okay. So, 1 by n I will take it out, this is n1 by n, that is minus x1, or minus of 1 by n comes out 1 minus x1, okay. And that is equal to 1 minus x1 is nothing but x2. So, this will be minus x2 by n, right. Or in other words, if I am looking at so this is just this quantity, right. So, if I am looking at dou n times dou x2 by dou n1, right. So, this is the clean way of solving this, right. So, this is equal to minus x2, okay. So, let us go back and rewrite this. So I need to find so number 1, which is nothing but dou g by dou n1, right. So I am finding out what mu1 is. So that is small g plus capital X2 times dou g by dou x2, or I think there is a minus there, right. So small g mu1 is equal to small g minus x2 times dou g by dou x2, right. All right. So what does this mean? Okay. So this is what we have derived, right, x2 x2. Okay. Now I have a function, right. So I'm going to write g of alpha. Alpha is, for now I am going to use all phases of as alpha, but once the phase computation comes up, then I can change it, right, as a function of x2, right. So this is a curve that goes up like this. Okay. Then at this composition I want to find out what is mu1 of x2. Okay. Now what this is telling me is, okay, so you go there, you take the g there, you just read off the value, and from g you subtract x2 times the slope of this, right. So x2 times the slope of this, so you subtract this quantity, and that quantity turns out to be the g value here, right. So I mean you can actually derive it, you can actually see it graphically yourself, but g minus x2 times dou g by dou x2 will be the intercept of this line, of this slopey line, right. Now this guy here, that is my mu1 at x2, okay, and this guy here is my mu2 of x2, right. So you can also do the same calculation for mu2, and you will get that, and mu2 will actually be g of x2 plus 1 minus x2 times dou g by dou x2, right. So and then you are writing everything in terms of x2, right. So this will be mu2 of x2, this will be mu1 of x1, right. So what I essentially have is that in a g versus x diagram, at any given point, right, at any given x2, the mu's can be read off from the graph, but not simply as slopes, right. So earlier if I have a capital G versus n, then the mu will be dou g by dou n1 or dou g by dou n2 and so on and so forth. So for that I need a capital G versus n2 and capital G versus n1, right. So I need two different curves because n2 and n1 are independent of each other, right. But instead I have g versus x2, right. This is just one variable, right. So one variable x2, correct. So g is just dependent on x2, there is no capital N dependence of small g, okay. Now in that case I can just construct a tangent to this, right, and wherever this tangent hits this pole, the pole at x2 equal to 1, that is my mu2 of x2. Wherever the tangent hits this pole, that is my mu1 at x2, right. Mu1 at x2 is this, mu2 at x2 is this, right. So I draw a tangent at x2 to this curve, and wherever this tangent hits this pole, right. So this pole is x1 equal to 1 or x2 equal to 0. So this is x2 equal to 0 pole or x1 equal to 1, okay. So that is mu1 at x2, and wherever this pole hits this, that is mu2 at x2, okay. Now why are we going through all this pain, right? Okay, let us go back to this g versus x2, right. So g of alpha versus x2. Now I ask you the question, what is mu1, okay, when x2 equal to 0? x2 equal to 0 means it is a pure compound, it is not contaminated. So pure compound of 1, right. So I am just taking so I have bismuth and what is the other, let us say arsenic, right. So I am not mixing bismuth and arsenic, I just have pure bismuth, right, and pure bismuth has some rhombohedral phase. So that is my alpha phase, right. So now pure bismuth without contaminating it with arsenic, right. So, no contamination with arsenic. Right. Now, I am asking the question, if I give you a G of alpha where this is pure bismuth, this is pure arsenic, right. So, that looks like this, and I ask you the question, what is the mu 1 or mu of bismuth in the alpha phase, right. Now, what is the answer? This is pure bismuth, right, at x2 equal to 0, x2 equal to 0 is pure bismuth, right. And there so it is actually just the mu of bismuth, right. So, it is pure bismuth. So, I am adding one more bismuth atom to the same pure bismuth, but I can also take a slope here at x2 equal to 0, and that is nothing but just that point, that is mu 1, right, of pure bismuth, and pure bismuth I am just going to write it as mu 1 tilde, right. Mu 1 tilde is mu 1 of pure bismuth. And bismuth is my species 1, right. Similarly, mu in the alpha phase, right. So, alpha phase, so I am just looking at the free energy of the alpha phase, the average free energy. This is not this is not some quantity which is it's just the average free energy. We have defined it, right. So, we have defined it as G by capital N, okay. So, now I ask you, what is the average free energy, or so what is the chemical potential or mu alpha in this phase, right. So, looking at the average free energy curve of this phase of arsenic when x2 equal to 1, this is pure arsenic, right, and that is this point where this goes and hits this pole, the other pole, the arsenic pole, right. So, this is a bismuth pole, this is the arsenic pole, and from here to here it evolves from bismuth to arsenic, or x2 is increasing, okay. So, and it hits the arsenic pole at mu 2 tilde, right. So, that is going to be mu 2 tilde. So, this is pure mu's, okay, all right. So, now let us hang on there, okay. G of alpha again as a function of x2, right, is going to be somewhat like this. Sorry, let me draw the poles closer, okay. And I said this is actually mu 1 tilde, this is actually mu 2 tilde, okay. If I have pure bismuth or pure arsenic, these are the mu's, right, these are the chemical potentials, right, okay. But now I am saying at any x2, right. So, this is a contaminated x2, this is a contaminated compound, not pure, right, which means bismuth is contaminated with arsenic or arsenic is contaminated with bismuth, right. So, depending on whether I am seeing 0.5 this way or 0.5 so whether I am seeing on left side of 0.5 or right side of 0.5, okay. So, what is contaminated, right. So, it is no longer a pure material, now this is a solution, right. Bismuth is going and mixing with arsenic, and both bismuth and arsenic together are forming one phase, right. So, now it has formed a solution. Now, in the solution, look, the mu's, mu 1 of mu of bismuth at x2 is actually less than mu in the alpha phase of bismuth at x2 equal to 0, right, in the alpha phase. Similarly, mu of arsenic at x2 is less than mu of arsenic, I should just compare mu of arsenic with mu of arsenic in pure arsenic phase, right. So, compared to pure phases, right, given that my G of alpha is a convex up function, looks like my contaminated phases emit more energy upon addition of an atom or 2 compared to pure phases. Mu is less, meaning mu is more negative, right. So, mu of arsenic at x2, which is a contaminated composition, this is contaminated composition, right. So, mu of arsenic in alpha, right, at x2, which is contaminated with bismuth, is more negative than mu of arsenic in pure alpha, right. So, mu of arsenic in pure arsenic, which is in the alpha phase. Okay. Oh, so that is good, right. So, what essentially I am saying is somehow materials like so more energy is released, which means so material likes to contaminate itself, right. So, somehow it appears as if somehow materials like to contaminate and form solutions rather than be pure. It appears, right. So, let us actually look at that, right. So, okay. Now, let us define another, so to explore this a bit more, let us define, so I have G as a function of x2, right. So, that goes like this. Now, I am just going to define G of a solution or G of mixing, right. So, I am going to mix 1 and 2, right. So, I am going to contaminate 1 and 2, right. So, that is equal to G minus, right, or let me come this way. Instead of defining G, I am first going to define mu 1 in the mix, mu 1 mix, right. So, mu so that is equal to mu 1, this is at any x2, right. So, I am actually looking at, you see, the mu 1 at x2 is this, right, but mu 1 pure is this. Okay. There is some energy difference there, I am gaining some energy, right. So, there is some energy difference in the in a way that I want it to be, right. So, I am releasing more energy. So, I want to bond with more of x2 somehow, right, when I am in a solution phase rather than when I am pure. Okay. So, I am just going to define that as mu 1 mix. Mu 1 mix is just mu 1 at x2 minus mu 1 of pure, right. So, mu 1 tilde, that is this quantity, that is mu 1 mix, right. Similarly, once I contaminate arsenic with bismuth, right. So, this is mu 2 of x2 and this is mu 2 pure, right. So, I can also define mu 2 mix is equal to mu 2 of x2 minus mu 2 tilde. Okay. Okay. So, these are the mixed mu 1s and mu 2s, right. So, keep them in mind. So, I am not now I have moved away from just the chemical potentials of species to what's the so what is the difference between the chemical potential in a solution minus the difference in a difference of chemical potential when I have a pure compound, pure material, right. So, similarly, what is the difference in chemical potential of species 2 in a solution when it is contaminated, when arsenic is contaminated with bismuth, how different is it from the chemical potential of a pure arsenic, right. So, these are the quantities, the mu 1 mix and mu 2 mix are what tells me something about the solution in some sense. Okay. All right. Now, I know what G mix is. G mix is nothing but so G so G minus, I have so mu 1 tilde, but I have only x1 fraction of mu 1 minus x2 fraction of mu 2, right, and that is nothing but so G in itself is x1 mu 1 minus plus x2 mu 2 minus x1 mu 1 tilde minus x2 mu 2 tilde, right. So, G mix is x1 mu 1 minus mu 1 tilde plus x2 mu 2 minus mu 2 tilde, and that is x1 mu 1 mix. I am writing mix on the top, is it? Okay. Let me write mix here because I will write the phase there, right. So, mix. Okay. So, plus x2 mu 2 mix. Okay, good. So, and both are negative numbers, right. So, so if I ask you the question then, now what is G mix, right. Now G mix I have removed the pure compounds, right. So, the chemical potentials of pure compounds or the G's of pure compounds, this is G of pure, average G of pure compound, right. So, G of G total G minus G of pure compound, that is G mix, right. Now what I am saying is essentially, so what is driving me to form a solution, right. So, I have two pure phases, right. So, 1 plus 2, this is pure 1, this is pure 2. It is forming a solution which is so 1 2 is my solution of composition X2. Okay. So, the way I have defined G mix is the G of this reaction, delta G of this reaction, right. So, G12 which is G, right. So, G of the solution minus G1 minus G2, right. So, this is pure G's, this is pure G's, this is G of the solution, G in the solution, average G in the solution. Okay. So, G mix is then is nothing but so if I write this in this chemical reaction form, 1 and 2, pure 1 and 2 are now contaminating to form a solution of 1 2, right. So, G mix tells me the driving force, right, or so the delta G for this reaction, right. So, that is so if the delta G is negative, then that forms for me a driving force for pure compounds, pure materials to mix and contaminate. Okay. So far it is a bit dry, but so we will put in examples and then actually show you properly what this means. But G mix, so it makes sense to define what G mix is, because G mix is just the pure driving force for the solution to form. Okay. So, it is not the G of the solution, G of the solution is G12, right. So, that is a curve like this, this is G12, right. It is not either G G1 or G, this is G1, this is G2, or mu1 and mu2, right. What I am saying is I define a G mix. Okay. So, now what is, if I ask you the question, let us plot each of these terms, right. So, G12 has been plotted. Okay. Now, what is G1 plus G2 as a function of or let us plot it in the same curve, that becomes more illustrative. This is G12, right. So, G12 is just the G, right. So, this is the average G, capital G by N, right. So, this is the average Gibbs free energy. Okay. Now, I am going to plot in green, right, in that is green color, yes, G1 plus G2 as I wrote here. Now, what is G1 plus G2? G1 plus G2 is mu1 tilde, right, because G1 is pure 1 and G2 is pure 2. Now, when I put, so how do I interpret this? When I put 1 and 2 as pure compounds, will they mix to form a solution or will they be separate, right. So, will they exist? Will 1 and 2 exist separately or will they form a solution? If they exist separately, G1 plus G2, right. So, G1 is pure 1, that is I have X1 composition of pure 1 and pure 1 so has a chemical potential of mu1 tilde, right. So, G1 will be X1 mu1 plus X2 mu2, right. Now, X1 mu1 plus X2 mu2 is this curve, right, given at any X2, this is the X2 of interest for me. At that X2, X1 mu1 plus X2 mu2 has this value, right. So, this is G1 plus G2 at X2, whereas this is G12 at X2, right. And the question for you is, will the solution form? Of course, it will form because I have so much of delta G, or delta small g. Okay. So, I have so much of advantage by forming a solution, right. So, I will form a solution, right, and so this is pure materials coexisting, and this is a solution, right, and at any given x2, right. So, will these two materials exist as 1 and 2 with different phase fractions, or will these two materials mix to form a solution, right. And apparently if this is the curve, I have this delta g or delta capital G delta small g, and the delta small g is nothing but my G mix, right. So, G mix defines for me the driving force for 1 and 2 to combine and form a solution, right, or one phase. They will mix, they will contaminate each other and form one phase, right. So, that is G mix. Okay. So, this is pure 1, this is pure 2. Now, it is no longer, the bismuth is no longer pure, arsenic is no longer pure, they have mixed with each other, and they have become a nice solution. Okay. So, it is no longer that the wife is separate, husband is separate, wife and husband have mixed, they have married, and now they are one entity, they are a solution. Now, their thermodynamics goes together, right. Is there any advantage of that? Yes, of course, so marriage has its own advantages, right. So, I do not want to list them out, but that is the G mix, right. So, if I have a G mix advantage, I will marry, and the wife and husband are now in one solution. So, their thermodynamics is different from the wife who was separate before marriage, the husband who was separate before marriage, and then so that dynamics is different, right. But is there any advantage of mixing them? Of course, there seems to be an advantage, and there is an advantage only. Why is there an advantage? This is the delta G of mixing, right, only because I have a convex down G mix, I have a convex down G, right, as a function of x2, correct. And that is always below this line. This line is the pure line, right. I am just mixing a pure 1 and pure 2, and they are not reacting with each other. Species in 1 is not moving into 2 into the crystal structure of 2, 2 is not moving into the crystal structure of 1. They are just separate. They are just they are minding their own business. They are not talking to each other, right. Now, is that a favorable state for me, or is mixing a favorable state for me, right. Now, let us say this is water, this is sugar, right. Water and sugar do not have to mix, right. So, water and sugar can exist separately. When I put them together, water can be in just like water, sugar can be just like sugar, they do not have to mix and form that solution, right. However, if they form that solution, I have this extra G mix, right. So, I have this driving force G mix which makes them form a solution, right. So, then I cannot separate out water and sugar or water and salt, whatever it is. Okay. So, that forms a solution. So, water likes to contaminate itself with sugar, right. Similarly, I mean you will look at lot of examples. If I am making hafnium oxide and zirconium oxide, right. Now, generally so hafnium oxide and zirconium oxide like each other so much that they would like to contaminate each other with each other, right. So, I will start forming solutions of hafnium oxide and zirconium oxide, right. Similarly, platinum and palladium, they would like to form solutions, right, rather than existing as platinum separately and palladium separately. So, if I want to make a thin film of hafnium oxide, and on the top of which I want to make a thin film of zirconium oxide, and both of them separated by a nice flat atomic interface, right, it may be difficult because so this may be difficult. Why? Because hafnium oxide and zirconium oxide would like to form a solution. So, they will form a solution here, let us say, right. So, they want to form a solution. It is no longer pure hafnium oxide or pure zirconium oxide, they want to form a solution, right. So, this is something that one needs to take into account, the solution thermodynamics. Okay. All right. Now, they will form a solution, of course, only when the G is solution or G mix is negative, G mix is the driving force to form the solution, only if G is convex down, right. So, if G is like this now. Okay. Now, imagine a scenario, we will actually look at this, where G as a function of x2 is not convex down, but it is convex up or something like this, right. So, G as a function of x2 is like this. Okay. This is possible, I mean it is not impossible, we will look at what conditions make it possible, right. So, G is now like this. Okay. Now, if I actually look at any given x2, right. So, this is the G of the solution, and if these two exist as pure compounds or pure materials, if 1 and 2 exist as pure materials, this is G of pure materials. So, now the solution would want to split into pure materials, or sorry 1 2, so no, I do not want to write G's here, 1 and 2, 1 2 solution. Now, this is no longer not a stable solution, this is like water and oil, they will not form a stable solution, they will rather separate out, right. So, this is pure 1 and this is pure 2, right. So, they would rather they would separate, right. Turns out oil hates water. So, of course, oil does not want to mix with water. So, if I hate someone, I will not form a solution with them, right. So, oil segregates out from water. Right. In that scenario, the G's will be this convex up functions. Okay. All right, very good. That is good. Okay. So, now what do you want to call G mix as? G mix is going to be called the mixing free energy, right. It is not the free energy of the solution, but it is the driving force to mix, and this tells me the driving force or negative of it, right. So, we wanted to make driving forces positive numbers, right. So, driving force to mix, right. So, that delta capital G will be minus G mix. Okay. All right, or minus n times G mix, right. So, this is the driving force we have defined, So, n times G will be so I can write G mix is equal to n times G mix. So, the driving force to mix will be delta G equal to minus n times G mix. Okay. So, this is the chemical driving force to make a solution from pure compounds. Let me again write it, I am repeating it so many times because it is quite important to appreciate that I have a chemical driving force. Okay. So, 1 wants to go and bond with 2, 2 wants to come and bond with 1, right. So, they do not want to be separate, they want to contaminate each other, right. So, they want to be good friends with each other. So, chemical driving force to make a solution from pure compounds. Right. Okay. Now, let me ask you this question as to, I mean we can also plot G mix then instead of G as a function of x2, right. So, and then remember that G mix is just G which is like this minus this line which is the pure G, G pure, right, and that will be a more symmetric curve, right. So, it is going to be like this. Okay. So, G mix, I mean it does not need to be symmetric about x2 equal to 0.5, that is not necessary in general, but so I can just, how does the driving force look? So, it will have the same intercepts here and here because I have subtracted the pure compounds, right. So, it is going to be like this. We'll look at this, how does it approach the poles very soon, but so G mix is going to be like this, right. So this line then becomes a flat line. Okay. So I can plot G mix as a function of x2 also, not just G as a function of x2, but G mix as a function of x2, all right. Okay, fine. So with that, so just to graphically understand, so what is G mix, so we can so we can do this exercise, and then so we have defined what G mix is in this class, and G mix is nothing but it's a driving force for my solution to form from pure compounds. Okay. So keep this in mind, and we will further develop this idea in the next class. Okay. All right. Thank you very much. I will see you in the next class.